Happy day. Myself, Dr. B. Kamalapriya. Today, I'm going to talk on the topic differential equations. So let us see what is the definition for differential equation. An equation that contains the derivative of one or more dependent variables with respect to the one or more independent variable. So when we deal with the differential equation, it is important to include these two variables. As the name suggests, when a factor is depending on another factor, we call it as a dependent variable. And when we have a variable which does not depend on the other variable, we call it as an independent variable. For example, we can take the independent variable to be a time. So here are the few examples for the differential equations. dy by dx is equal to 2xy. So here x is our independent variable and y the dependent variable. And the last equation, dou square z by dou y square is equal to a square dou square z by dou x square is an example of partial differential equation. Now, let me tell you what you mean by a differential equation and where do we apply it in our real life. So, when we eat an ice cream and when the ice cream comes in contact with a room temperature, it starts to melt. So, as soon as the ice cream starts melting, we'll keep our motion fast in order to complete our ice cream. So, here I'm taking the equation dt by dt is equal to k times of m minus t, where the capital T indicates the temperature of an object. Here our object is going to be the ice cream, the temperature of the ice cream, and m is the temperature of its surrounding. When it comes in contact with the room temperature, it starts to melt. So that is the temperature of our surrounding, and t is the time. Time here is an independent variable and the temperature of an object is an dependent variable. The dependent variable, it depends upon the time and it starts to melt. So what we will do, what can we find from this? How long will it take for the ice cream to melt completely? So we give the proportionality constant by k. Moving on to the next example, when we are in a particular point and we want to reach a destination, so through some vehicle, let's take to be a car. So we are traveling for a distance of some 8 kilometers that has been indicated here, and it takes 15 minutes to reach your destination. So how do you calculate your speed or velocity? So it is given by dx by dt, where x is the distance that we have traveled and t is the time taken. So the time here is our independent variable and x is the distance that we have covered here. So these type of examples and many real life applications, we implement the differential equation in order to calculate the thing that we need. The next one is order of differential equations. So when we write a differential equation, we need to find what is the order of that particular differential equation and the degree of the differential equation. So coming to the definition of order of differential equation, the order of differential equation is the order of highest order derivative present in the equation. For example, if I am considering the equation dy by dx is equal to 3x plus 2, where my x is an independent variable and y is a dependent variable, here the derivative dy by dx is of first order because it is being derived for one time. When I get the second equation, it is d square x by dy square plus 2 times of dy by dx plus y is equal to 0. When I consider this particular equation, the order of this equation is 2. So we have the second order derivative and first order derivative in this equation, but when we consider the order of the equation, we will be taking the highest order derivative. So this equation is of order 2. And the next equation is dy by dx plus y is equal to kt, where again we have only the first order derivative. So we call this particular equation to be the of order 1. So next one is degree of differential equation. So what do you mean by a degree of differential equation is it is the power of the highest order derivative. Wherein originally the differential equation can be represented in a polynomial form, where the derivatives dy by dx can be represented in the form of y dash, y double dash, and it goes on, where y dash represents the first order and double dash the second order. So when I take the example of dy by dx plus 1 is equal to 0, the order of this particular equation is 1. We have to check the degree of the highest order. So the highest order for this equation is 1 and the power is also 1. So this equation is of degree 1. When I go for the second equation, it is y triple dash power cube plus 3y double dash plus 6y dash minus 12. So this equation is of order 3. Now I have to check the highest order of this equation and the highest order is again going to be 3. So next thing that I have to check is the power of the highest order. So the power of the highest order is 3. So the degree of this particular equation is 3. Let me classify the differential equation. So differential equation is basically broadly classified into two types, is ordinary differential equation and partial differential equation. So the ordinary differential equation again can be classified as first order, second order, and it goes on up to higher order. Similarly, the partial differential equation can also be classified into first order, second order, and higher order. The higher order derivatives can again be classified as linear and non-linear differential equations. So the linear differential equation, it can be subclassified as homogeneous and inhomogeneous differential equation. So what do you mean by an ordinary differential equation? An ordinary differential equation which contains only ordinary derivative of one or more dependent variable of a single independent variable. So when you take this example, dy by dx plus 5y is equal to e power x. Here x is to be the independent variable and y is our dependent variable. So when I take the second equation, dx by dt plus dy by dt is equal to 2x plus y. Here t is our independent variable and we have two dependent variable x and y. So these type of differential equations, we call it as an ordinary differential equations. So the next one is partial differential equations. So an equation that contains partial derivative of one or more dependent variables of two or more independent variable. So basically a partial differential equations need minimum of two independent variables and it can be of more. For example, dou square u by dou x square plus dou square u by dou t square is equal to 2 dou u by dou t. Here my x and t are to be the independent variable and u is the dependent variable. So now I will be discussing about two types of ordinary differential equations and how do we solve it. So the first type is going to be first order linear ordinary differential equation. When we have a differential equation of the form like dy by dx plus py is equal to qx, when we have a differential equation of this form, this can be solved and the general solution is given by y is equal to integral u of x q of x plus a constant divided by u of x. So what is u of x? U of x is nothing but it is the exponential of integral p dx. So this particular factor is called as an integrating factor and we will see an example how do we solve this type of a first order linear ODE. So here the problem is dy by dx plus y cos x is equal to half sin 2x. So we have to check what is our p. So p is given as cos x and q is half sin 2x. Now we need to find our integrating factor, that is integral p dx which is sin x and exponential integral p dx is e power sin x. The solution is given in the format of y e power sin x is equal to integral of your q of x, that is half sin 2x, and your integrating factor e to the power of sin x dx plus constant. So when we integrate it, we have e power sin x and sin 2x, when we integrate it, we will be left with 2 sin x cos x and the 2 will get cancelled. And now I am replacing my sin x by z. So integral of e power z, z of dz plus a constant. So when you integrate this particular factor, you will be left with e power z of z minus 1 plus c and you are replacing the z value by sin x. So it is e power sin x into sin x minus 1 plus the constant. So the next type of equation is called as a Bernoulli's equation. When we have a differential equation of the form dy by dx plus p of y is equal to q times of y power n. So where p and q are considered to be the continuous functions. Differential equation of this type is called as Bernoulli's equation. When we have a differential equation of this form, while solving, the first step that we will happen to do is you have to divide the differential equation by y power minus n. So the reduced equation will be of the form y to the power of minus n dy by dx plus p times of y to the power of 1 minus n is equal to q. Then I am substituting z is equal to y to the power of 1 minus n. So I will get the reduced equation of the form dz by dx plus p times of z into 1 minus n is equal to q times of 1 minus n. We will see an example for this Bernoulli's equation. Here the question is dy by dx minus y times of tan x is equal to sin x cos square x by y square. So as I stated, I have to divide this by y power minus n. Here I am taking it to be y square. So if I divide it by y square, I will be left with y square dy by dx minus y cube tan x is equal to sin x cos square x. So what I do now is I am substituting z is equal to y cube. So I will get the reduced equation as dz dx minus 3 times of z tan x is equal to 3 sin x cos square x. So now my p is minus 3 tan x here and my q is 3 sin x cos square x. So integrating the p dx, I am left with log cos cube x and e power integral p dx is cos cube x. So z of cos cube x is equal to 3 times of integral sin x cos power 5x dx and plus constant. Now replacing my z by y cube, I am left with y cube cos cube x is equal to minus cos power 6x by 2 plus the constant. So moving on to the next topic is linear differential equation with constant coefficient. So far we saw the ordinary differential equation. Here again the linear differential equation which has a coefficient as constant. So a typical linear equation of second order, since the derivative, highest derivative over here is 2, I am taking a typical linear equation of second order with a constant coefficient, where my constants are represented as a, b, c, and capital X is a function of small x. Now I am considering the equation of this form 2, that is a d square y by dx square plus b dy by dx plus cy is equal to 0. I am removing the function x and I am replacing it with 0. So when I find the solution for this particular equation 2, this solution is going to be the complementary function of 1. So in order to solve the equation 1, you have to equate it first to 0 and you will be finding the solution for that one. That particular part is called as the complementary function of the differential equation that we are finding. So how do we solve? How do I find the complementary function? Now to solve that particular equation, I have to assume the trial solution. Like if I am taking y is equal to e power mx for some values of m, my first derivative will be m into e power x. My second derivative is m square e power x. And substituting these values again in the equation 2, I will be left with e power mx times of am square plus bm plus c is equal to 0. Such that it satisfies the condition am square plus bm plus c is equal to 0. And this particular equation, that is am square plus bm plus c is equal to 0, is called as the auxiliary equation. So in this auxiliary equation, 3 cases arises. So what are the 3 cases are? The first case when the roots are real and distinct, and the second case is like the roots are real and they are equal. The third case, the roots are imaginary. So we will go through each cases. So the first case, when my roots are equal and my roots are real and distinct, I am taking the roots to be m1 and m2. That is y is equal to e power m1x and y is equal to e power m2x. And this is the solution of the differential equation that we have taken. Thus, the general solution can be represented in the form of y is equal to a times of e power m1x plus b times of e power m2x. So a and b are the arbitrary constants here. So we will see an example for that. The question given is a second order linear differential equation with constant coefficient. The highest order is second, 2 and plus 5 dy by dx plus 4y is equal to 0. Now I am writing the auxiliary equation for this particular differential equation. It can be written as m square plus 5m plus 4 is equal to 0. On solving, I will be arriving at the m values to be 1 and 4. Here my roots are real and they are distinct. So I am writing the general solution as y is equal to a e power x because my m1 is 1 plus b e power 4x, my m2 is 4. So the second case is my roots are real and they are equal. So I am taking my roots to be m1 and m2 and they are equal. So m1 is equal to m2. Thus the general solution we usually write it as y is equal to a e power m1x plus b e power m2x. Since m1, m2 they both are equal, it can be written as y is equal to e power m1x times of a plus b of x. So when you consider this example, so we have the second order linear differential equation and the auxiliary equation for this one can be written as m square plus 2m plus 1 is equal to 0. When I solve this quadratic equation, I will be left with the roots m is equal to minus 1 occurring twice. So how do you write the general solution? Y is equal to e power minus x since my m is minus 1 times of a plus b of x. So the third case is let the roots be imaginary. So how do we write our imaginary roots? They usually occur in pair. So m1 is equal to alpha plus I beta and m2 is equal to alpha minus I beta. So the solution can be written as y is equal to a e power alpha plus I beta x plus b e power alpha minus I beta x. So this can be written as y is equal to e power alpha x times of c cos beta x plus d sin beta x. So again c and d are arbitrary functions here. So when I consider the example, second order differential equation d square y by dx square minus 3 dy by dx plus 5y is equal to 0. When I write it in the form of auxiliary equation, I have m square minus 3m plus 5. So when I solve this quadratic equation with the discriminant part, we have m to be 3 plus or minus root 11 I by 2. So the real part here is 3 by 2 and the imaginary part is root 11 by 2. While writing the general solution, y is equal to e power 3 by 2x, that is your alpha value, alpha is 3 by 2, and a sine of root 11 by 12x, and that is your beta value, plus b cos of root 11 by 2x. So usually the solution of the differential equation, they have two parts, like y is equal to complementary function and particular integral. So far that we saw is how do we find the complementary function. So when it comes to particular integral, so the particular integral will be written in the form of 1 by the differential equation times the function. So the function x is being represented. Depending upon the types of function, there are different methods to solve the particular integral. So as a whole, the differential equation solution can be written as y is equal to complementary function part plus the particular integral. So these are some books for reference that initially can be used for studying differential equation. It is S. Narayanan and T. K. Manikavashagam Pillai, Calculus Volume 3. It's a differential equation in Fourier series, and P. R. Whittle, differential equation and Laplace transforms, and an introduction to ordinary differential equation by Codington. Thank you.